How should a satellite be launched so that it... Introduction to satellite. Satellite is a celestial body that revolves constantly around another celestial body. In our solar system, different planets revolve around the Sun. So, planets can be said to be the natural satellites of the Sun. The Moon is the natural satellite of the Earth. So far, many artificial satellites, that is, man-made satellites, have been launched. The satellites are put into their respective orbits with the help of multi-stage rockets. Artificial satellites are used for communication purposes, for weather forecasting, to study various phenomena in the outer regions of the Earth's atmosphere, for topographical purposes. A satellite which remains stationary with respect to a fixed point on the surface of the Earth is called a geostationary satellite. These satellites are used for communication purposes. The application of satellite in everyday life has become so immense that the study of satellites is essential. In this lesson, you will be able to derive an expression for the velocity of a satellite, learn the paths of a satellite when launched with different velocities, learn about geostationary satellite and understand the conditions for a satellite to be geostationary, learn the definition of escape speed and derive an expression for it, and understand the concept of escape speed. How should a satellite be launched so that it goes around the Earth in a circular path? To launch a satellite, it must be taken to the required height above the Earth's surface. The satellite is then launched with a particular velocity so that it orbits the Earth in a circular path. For a satellite to be in circular orbit around the Earth, it should be launched with a velocity in the horizontal direction relative to the Earth.
So this means that in the horizontal direction, this means that there is the motion. The satellite motion must be same direction with the Earth, so that the satellite will move or rotate with the same axis to the Earth.
Let a satellite of mass m be launched horizontally relative to the Earth's surface with a velocity v. The centripetal force required for a stable circular path of the satellite is provided by the gravitational force of attraction between the Earth and the satellite. Centripetal force equals gravitational force, which implies mv square over r equals gmem over r square, which implies v equals square root of gme over r, where me is the mass of the Earth, m is the mass of the satellite, and r is the radius of the satellite's orbit.
Okay, so we look at here, the satellite will always orbit the rotate around the Earth. This because the satellite with the gravitational force, attracted by the gravitational force by the Earth. So this gravitational force attract to the center of the Earth and cause the satellite will not move away from the Earth. Second, the gravitation, the satellite is always orbit the Earth, right? So this means that in the circular motion, there will be a centripetal force. that add to the satellite, that cause the satellite always orbit around the Earth. So from here, let's say this is what is the function of the formula? We use the concept of centripetal force equal to the gravitational force. So from here, we notice that let's say this is the Earth and this is the satellite. When the satellite is launched, we consider there will be a distance where this is the R. This is the distance of R. So from here, we can notice that this is the height of the satellite and this will be the radius of the Earth. So from here, we have two things we need to consider. That means this is a height from the surface of the ground, and we have also the RE that will be the radius of the Earth, RE. So from here, gravitational force that act on the satellite will equal to the centripetal force that act on the satellite. So from here, we get that the speed or the velocity of the satellite is equal to square root of gme over r. Mg over r, me, that means the mass. It depends on the mass of the Earth. It depends on the distance from the satellite to the center of the Earth. Let's say, as we know that we have around more than a few hundred countries around the world. So from here, if every country launch more than one satellite, that means that we have few hundred or maybe more than 1,000 of satellite around the Earth. So from here, what will happen? The number of the satellite is quite much, and maybe the satellite will collide each other, right? So if like that, that means that this is the Earth. The satellite launch, they cannot launch all together with the same radius. So there some must be lower, some must be higher, with different height. If with different height, that means that if, let's say the circle, from a circle, we notice that, let's say this is the big circle and the circle, the radius will be smaller. So if different height, they will have different circumference. Different circumference, different height means that the satellites must launch with different velocity. Once the satellite is launched to a certain height, so we need to consider, we need to set how much of the velocity of the satellite so that the satellite will always revolve or move around the Earth without fall back to the Earth or without fly away from the Earth. Okay, let's move to the next slide.
Click on Case 1 to observe the path of the satellite if the launch velocity is slightly lesser than square root of gme over r.
That means that here, if we wish to launch to a certain height of r, we set the r already. So that means we get the value of v. If we launch with greater velocity, that means that the velocity of the satellite greater than the v we calculate. So what happened to the satellite? Observe the motion of the satellite when it's revolved around the Earth.
If v is less than square root of gme over r, the satellite will orbit in an elliptical path with Earth as the far focus. Weather satellites are purposely launched into an elliptical path.
Okay, sometimes the scientists, they need to launch it with the elliptical path because maybe they don't want the satellite always follow the Earth. Maybe they wish to do some purpose, maybe for forecast and so on. Oh, for the geography, okay, geography observation. So from here, that means that if the satellite launch less than the velocity v, that means that it will move in an elliptical path. We launch here, if less, that means that this will move further. The distance is higher. Okay, reader.
Click on Case 2 to observe the path of the satellite if the launch velocity is greater than square root of gme over r.
Okay, how about if we launch with a velocity greater than the exact velocity? So this means that we notice that it will move with an elliptical path, but the greater distance will be at
V
the other
is
side.
greater than square root of g me over r, the satellite will orbit in an elliptical path with Earth as the near focus.
So near focus or far focus, that's not important. But we can confirm that it's not at the same focus point with the Earth.
What is a geostationary satellite? Click Answer to find out.
So what is meant by geostationary satellite? Geo comes from the words of the geography. Stationary, this means that not moving. This means that when the satellite is revolve around the Earth, they will always follow a point on the Earth. This means that this that is the geostationary satellite. This means that if Malaysia launch a satellite for the telecommunication purpose, this means that we wish the satellite always follow Malaysia, right? So impossible that we launch a satellite at the end, the satellite go to other country. So this means that we don't want. So this type of satellite, we call that is the geostationary satellite.
As the Earth rotates, geostationary satellite moves in its orbit following the rotation of the Earth. Actually, the satellite seems to be stationary with respect to a fixed point on the surface of the Earth. This is the reason why the satellite is called geostationary satellite or synchronous satellite.
Okay, this type of satellite, geostationary satellite, or we call it synchronous satellite. So this satellite mostly used for communication purpose. We have another satellite, we call that non-geostationary satellite. This means that the satellite are moved randomly, are moved freely. So mostly that type of the satellite is used for the forecast or used for the research to the geography or research to the Earth and so on. That means that we wish to move any point on the Earth we want.
Click Conditions to know the conditions for a satellite to be geostationary.
So what are the conditions?
Condition 1. The satellite orbit should be concentric and coplanar with the Earth's equator. Condition 2. Direction of rotation of the satellite around the Earth should be the same as the direction of rotation of the Earth. Condition 3. Period of the geostationary satellite should be the same as the period of the Earth's rotation about its axis.
So we have three conditions. First, they must be in the same direction. Second, they should be follow a point on the Earth. And next, the period of the satellite must be same with the period of the Earth. That means that there is one revolution with 24 hours. Okay.
Click Height to know the height of a geostationary satellite. Height of the satellite from the surface of the Earth is 3.6 times 10 to the power 7 meters.
So the satellite we launch normally is 3.6 times 10 to the power 7 meter. This one is for the geostationary satellite. If others than that, that means that if non-geostationary, that means they can launch either higher a bit or lower a bit, but they must still in the gravitational within the gravitational field. So if with the gravitational field, that means that cannot be too near to the Earth, otherwise the satellite will fall down. If too far away from the Earth, that means that the satellite will lose attraction from the Earth. So that means it will fly away.
For a satellite to orbit in a stable circular path around the Earth, the centripetal force is provided by the gravitational attraction of the Earth. Centripetal force F equals mr omega square. Since omega equals 2 pi over t, F equals 4 pi square times mr over t square. Earth's gravitational force on the satellite F equals g MEM over r square, which implies 4 pi square times mr over t square equals g MEM over r square, which implies r equals g ME t square over 4 pi square the whole power 1 over 3. For a geostationary satellite, t equals 24 hours, which equals 86,400 seconds. G equals 9.81 meter per second square. Using the expression for small r, the calculated value of small r equals 4.24 times 10 to the power 7 meters. R plus h equals 4.24 times 10 to the power 7 meters. Therefore, height of satellite from surface of the Earth, h, equals 4.24 times 10 to the power 7 minus 6.40 times 10 to the power 6 meters, which equals 3.60 times 10 to the power 7 meters.
Okay, so from the calculation, we get that, let's say this is the R. The R from the calculation, R is equal to 4.24 times 10 to the power 7 meter. Where this we need to deduct the RE. This will be the RE, and the height of the satellite is from the surface of the Earth. So this means that from here, this height of the satellite will be around 3.6 times 10 to the power 7 meter. So this means that this will be the value from the surface of the Earth to the satellite. Okay. Next.
Summary. The speed of a satellite in circular orbit at a distance r from the center of the Earth is v equals square root of g me over r. If the velocity is less than v, the satellite traces an elliptical path with the Earth as the far focus of the ellipse. If the velocity is greater than v, the satellite traces an elliptical path with the Earth as the near focus of the ellipse. A satellite which remains stationary with respect to a point on the Earth is called a geostationary satellite. The geostationary satellite is stationed at a height of about 36,000 kilometers above the equator. The conditions for a satellite to be geostationary are: the satellite orbit should be concentric and coplanar with the Earth's equator. The direction of rotation of the satellite around the Earth should be the same as the direction of rotation of the Earth. The period of the geostationary satellite should be the same as the period of the Earth's rotation about its axis. A satellite in circular orbit around the Earth possesses both gravitational potential energy and kinetic energy. Click GPE to know the expression for gravitational potential energy of a satellite. Gravitational potential energy U equals negative G MEM over R, where ME is the mass of the Earth, M is the mass of the satellite, R is the distance between the Earth and the satellite, and G is the universal gravitational constant. The expression for kinetic energy of the satellite can be determined using the concept that the centripetal force required by a satellite is provided by the gravitational attraction of the Earth. Click KE. Centripetal force mv square over r equals gmem over r square, which is the gravitational force, which implies mv square equals g mem over r. Kinetic energy K equals half mv square, which equals half g mem over r.
So this is the kinetic energy. When the satellite is moving, it possesses two types of energy. One is the kinetic energy. Another will be the gravitational potential energy. For a satellite is moving, around the Earth or revolving the Earth, its total energy is equal to the gravitational potential energy, the sum of the gravitational potential energy and the kinetic energy.
Click on GPE and KE to know the total energy.
The total energy is equal to gravitational potential energy, which equal to negative GMEM over R, plus with the kinetic
Total energy equals gravitational potential energy plus kinetic energy, which equals negative G MEM over R plus half G MEM over R, which equals negative G MEM over 2R.
So this means that at the end, we get that this will be, at the end, it will become negative 2GMEM over 2R. This will be the total energy. This is the potential energy. If gravitational potential energy is equal to, the magnitude is GMEM over R. This means that it will be negative because it's an attractive force. And and its kinetic energy will be 1 over 2 GMEM over R. This means that the total energy of the satellite at the end become negative GMEM over 2R.
Observe a satellite revolving around the Earth at a distance r from the center of the Earth. The kinetic energy K, gravitational potential energy U, and total energy E of a satellite depend on its radius of orbit as shown. E equals U plus K, which equals negative G MEM over 2R.
So no matter how the energy of a satellite reduce with the distance, no matter that is the kinetic energy or the gravitational potential energy or the total energy, all of the energy reduce with the distance increase. If the satellite is much further from the center of the Earth, the kinetic, not only the kinetic energy reduce, the gravitational potential energy also reduce. This means that the total energy of the satellite reduce with the distance.
To know what happens to the satellite when launched with different speeds, first select the speed 5 times 10 to the power 3 meter per second.
So this means that what happens if we launch a satellite with different speed? Okay. So this speed means that we launch from the Earth. That means that if they is from the we launch something, not only the satellite only. Okay, so if we launch, and let's say the satellite, we launch a satellite from the surface of the Earth to the space. So what will be the speed? The speed, we cannot set that, okay, I can launch any speed. If slower, maybe it takes longer time to reach to the space, or I launch faster, maybe it's reached to the space faster. No, these concepts are wrong. We cannot use we cannot think about this. So we need to have a certain speed according to the height of the satellite we wish to launch. So now observe that if I choose the speed, here we have 5 times 10 to the power 3, 5, 7, 9, 11, 13, and 15. So observe what will happen. Launching.
The missile crashes to the Earth.
So this means that the missile or the satellite will fall back and crash to the Earth.
Select 7 times 10 to the power 3 meter per second from the drop-down menu and observe again the trajectory of the missile. Is the launching velocity sufficient?
Observe the motion of the missile, yeah? So now I choose 7 times 10 to the power 3.
No, the missile again crashes to the Earth. Select 9 times 10 to the power 3 meter per second from the drop-down menu and observe the trajectory of the missile.
Now what happens if the launch speed or launch velocity is 9 times 10 to the power 3?
The missile moves in an elliptical orbit.
So that means that now this speed, this velocity is slightly less than the
Select 9 times 10 to the power 3 meter per second from the drop-down menu and observe the trajectory of the missile.
Okay, that means that now it's moved
The
with
missile moves in an elliptical orbit.
So now it's moved with an elliptical orbit, right? This means that this missile launched with a speed slightly less
Select
than the
9
speed.
times 10 to the power 3 meter per second from the drop-down menu and observe the trajectory of the missile. A missile fired upwards eventually falls back to the ground due to the Earth's gravitational attraction. Can a missile be projected to
again, yeah.
Select 9 times 10 to the power 3 meter per second from the drop-down menu and observe the trajectory of the missile.
I chose 9. Okay, just now we chose 9, right? So that means that it will launch and move in an elliptical shape.
The missile moves in an elliptical orbit. A missile fired upwards eventually falls back to the ground due to the Earth's gravitational attraction. Can a missile be projected to escape completely the gravitational pull of the Earth? Click Answer. Yes, provided the missile is projected with a certain minimum speed known as the escape speed. The escape speed of the Earth is the minimum speed of an object to escape completely the Earth's gravitational pull and move to infinity. Select 11 times 10 to the power 3 meter per second, 13 times 10 to the power 3 meter per second, and 15 times 10 to the power 3 meter per second from the drop-down menu and observe the trajectories.
So what is meant by the speed, escape speed of the Earth? So that is the minimum speed that required by an object to escape completely from the Earth. So this means that we need, if we launch something, we wish the object that can reach to the space, so we must launch with minimum speed. That is the escape velocity. Let's observe what will happen to the speed with 11 times 10 the power 3 ms negative 1. So missile is launching.
Missile escapes completely from the Earth's gravitational pull.
So this means that 11 completely escape.
The escape speed.
Okay.
The escape speed of the Earth
So
is the
let's
minimum
see.
speed of an object to escape completely the Earth's gravitational pull and move to infinity. Select 11 times 10 to the power 3 meter per second, 13 times 10 to the power 3 meter per second, and 15 times 10 to the power 3 meter per second from the drop-down menu and observe the trajectories.
So 11 just not escape, right? 11 it will escape.
Missile escapes completely from the Earth's gravitational pull.
So what will happen if 13?
Missile escapes completely from the Earth's gravitational pull. Missile escapes completely from the Earth's gravitational pull.
That means that if the satellite is projected with the minimum speed or the escape velocity greater than the escape velocity, that means that the object will free, they will escape totally from the gravitational pull. So this concept is like that. Let's say, okay, let's think about a concept of the escape velocity. So first, in case one, how we launch a let's say we wish to bring the astronaut from the surface of the Earth to the space. That means that normally we use a rocket, right? We use a rocket to bring the astronaut from the surface of the Earth to space. Okay, from the surface. So in this case, that means that we need the extra energy. We need to burn the fuel. We need to use a lot of the power to bring the astronaut which reach to the space. All this thing is controlled by the fuel, controlled by the rocket. That means that it's human-made, right? Against the gravity, right? So what you want to do, we can, the scientists, they all the, okay, for the pilot of the rocket, they can control the motion, they can control how much of the height or where they wish to go. But in the second case of the escape velocity, that means that at the surface of the Earth, okay, let's say surface of Earth. So now this astronaut, now we launch it. That means that easier, I give the simple example. We want to throw a stone. If we throw a stone upwards, that means that the stone will fall back to the Earth, right? So what is the speed we need to throw? That means that this stone will not fall back to the Earth. Okay, so the stone must be thrown with a speed of escape velocity. If I can throw the stone with the escape velocity, that's from the surface of the Earth, we throw, yeah, That means that this stone will totally escape or free from the gravitational pull. So we can move it that means that the stone will move to the space and escape and free from the gravitational pull. So this means that if we want to launch the no matter satellite or we want to launch the the astronaut without any rocket or without using any fuel, that means we throw the astronaut. That means that this once we throw starting, the initial speed must be equal to the escape velocity, so that this astronaut, we can throw the astronaut directly from the surface of the Earth to the space. So this is the concept of the escape velocity. Don't mix with the concept where we use a rocket to launch an astronaut. So this one we bring them, the rocket is supplied with the fuel and produce the extra energy, extra